walkthrough of TMUA practice paper number 1. Let's get straight into it. Question number 1 is a bit of expansion. Now, you could do polynomial division here. In fact, no, I'm talking about the wrong, I think I'm talking about question 2. Ignore me. Yeah, we can just binomially expand this. We've got the coefficients of 1, 3, 3, 1. Hopefully you recognize that from Pascal's triangle. Make sure you cube the whole of ax, not just the x bit. And you get this. Apparently that equals this, which means we can just straight up compare our coefficients. So a cubed must be 8, which gives us a as 2. No need to worry about the plus minus because it's a cube, not a square. The next easiest thing to look at is b cubed is this. Now, you can do some messing around with the indices here to make this make sense, but I think it's easy enough to see that it's going to be minus root 3, because minus root 3 times minus root 3 times minus root 3, well, the two root 3's are going to come together to give us this 3, and then the spare one is going to be there. 3 negatives make a negative, so that should be fine. We can now look at this middle bit. We actually don't even need this bit. We could look at this if we wanted to, but we don't need it. We're just going to look at this bit here. The x squared coefficients, that must be that. We know a and b, so we're going to put those in. A squared is 4, b is this, and we can solve. Get the answer. Nice. Next one. Yeah, so sorry, this is the one where you could divide this by x plus 2 using some polynomial division. I'm not going to. I'm just going to say this is equal to the factor times a quadratic that I don't know yet, but I'm going to work out. Because if I just expand this out, I'm actually not going to do that. If I were to expand that out, though, I think we could see that k must be 3. Because the only way you can get an x cubed when you expand this is to do this times this, and that gives you k must be 3. If you look over the other side, you can see that a must be 2 times n. Now that doesn't actually end up being that important, I don't think, but let's keep going. Looking at the x squareds, now we've got 13x squareds over here. How do we get x squareds over here? Well, we can either do x times mx for m lot of x, or we can do 2 times kx squared for 2k. So our coefficients over here for x squared are either going to be these two multiplied together for 2k as the coefficient, or these two for m. Now we know k is 3, so we can solve for m. And now if we look at the x's, we've got 8 x's over here. How many have we got over here? Well, I'll either do them by doing this thing to get n lots of them, or by doing this thing to get 2m lots of them. So 8 is going to be this 2m plus this n. But we know what m is, which means we can find n. And I think the question was, what's the complete factorization? Well, I know what k, that's 3, I know what m, that's 7, and I know what n are. So I'm just going to put those into my into here and say that this is factorized as this. Now, at this point, I could work out a, but I don't need to because it's asking me to just factorize this completely. And I can factorize this. Now, there's loads of different ways to do that. I tend to just kind of spot it and just figure out. But that's going to be the factorization, and it's going to be this one here. Good. Next one. So it's talking about a normal, so I know I'm going to have to differentiate this. To differentiate this, I'm going to need the power, not the divide by. So I'm going to flip it to be this, differentiate to be this, times by it, and then minus the power by 1. And now we're looking at x as 1. So at x is 1, dy by dx, well, anything to the power, well, 1 to the power anything is just 1, so dy by dx is minus 4. Now, if we've got a normal to this, a normal obviously meets at 90 degrees, so it's going to be a line with gradient 1 over 4, the negative reciprocal. So the equation of this normal is going to be y equals 1/4 x plus c, and it goes through the point x is 1. Now, that's only half a coordinate, but we can find the other half of the coordinate by putting it in here. If I put in x is 1 into this curve, I just get 2 divided by 1 squared, which is 2. So the y coordinate of this point is 2. So essentially we have a line meeting a curve at the point 1, 2. And this is the equation of the line so far, but I know it goes through 1, 2. So I can work out the rest of it, and I get c is 7/4. So I have the equation for the line now is this. Now it's saying the line cuts the x-axis of p and the y-axis of q. Well, I know where it cuts the y-axis. That's 7 over 4. So if I were to just quickly draw this, cuts the y-axis at 7 over 4. Where does it cut the x-axis? Well, it cuts the x-axis where y is 0. Like you're not moving up or down. So y is 0. Times both sides by 4, and you can solve that x is minus 7. And now we're looking for the length of p to q. So obviously this is going to be some Pythagoras with 7 and 7 over 4. Now you could set up some Pythagoras and say this length is d. I'm doing 7 squared and 7 over 4 squared. I put a minus in there just because, I mean, it doesn't make a difference. You square it out anyway. Now this is annoying to do. There is actually a much faster way of doing this without having to mess around with these fractions here, which is to notice that this triangle we're looking at, which has kind of length 7 over 4, so that's this triangle in the picture, length, height 7 over 4, width 7. That's just a scaled up version of this triangle, because notice how this length is this length divided by 4. Now, this triangle is much easier for me to work with. That's going to have a side length of root 17, because it's just 1 squared plus 4 squared, which is 17 square rooted. And now there's a scale factor between these two, which is you multiply by 7 over 4, right? To go from 1 to 7 over 4, scale factor 7 over 4. So RD is going to be 7 over 4 times this, which is in the answer somewhere. So yeah, if you can spot a simpler triangle, a simpler triple that you can do easily, that might save you from doing some complicated Pythagoras. Nice little trick. Okay. Yeah, whenever you see these questions, just work out the first few and hope something nice happens. So let's work out A1. That just is what happens when we put n is 1 everywhere. And we eventually get, well, the -1 to an odd power is -1 to an even power is +1, but that's a takeaway still there, so there's still a takeaway. And we get -3. That's fine, I guess. Let's try finding A2. Just put 2 in for all of these n's. And you end up with +3, so that's interesting. And now when you put in n is 3, because -1 doesn't change, the only way to change a -1 to the power is to make it odd or even. Putting 3 into here is essentially the same as putting 1 into there, because all that matters is this is odd, which means it becomes the same thing as this one did. This is even, which means it becomes the same thing this one did. And this power is odd, which means it becomes the same thing this one did. And so you get the same maths that you did here, and therefore the same answer. So what this sequence is going to do is it's going to go -3, 3, -3, 3, -3, 3, -3, 3. And when you add all those up, of course, they're all going to cancel, except you're starting at an odd number and ending on an odd number. So A1 will cancel with A2, and then A3 will cancel with A4, and so on and so on and so on, until A37 cancels with A38, because the odd number comes first. But then you have this random A39 left over. And so the answer is going to be -3. Number 5. Okay, so basically integration, except it's an integration with a bit of a twist. Now I can plot this graph. It's a parabola, obviously, quadratic. Cuts the y-axis at -1. Its roots, well, this is a difference of 2 squares, so I can find its roots are at 1 and -1 pretty easily. So there it is, and it's asking me to find the total area enclosed by the lines x -2 and x +2. So that's this bit there. So I'm looking for this area, this area, this area, and this area. Now, if I integrate just between 2 and -2, which you might be thinking, oh, that's the thing you do to find area. The problem is these negative areas that are below the axis count for negatives, like they are negatives, and they start cancelling with the positive areas. But they want me to find the total area enclosed. So they don't want any cancelling. So what I'm going to do instead is I'm just going to integrate between 2 and 1. And I'm sure if you're watching this video that you know how to integrate, so I'm not going to talk too much about this. I'm going to be good with my fractions there and make sure that I get those right. And I get 4/3. So this area is 4/3. Now I'm just going to integrate between 1 and 0. And the nice thing about choosing 0 as one of your inputs is it just immediately goes away when you put it in. And you get this. So this area is 4/3. This area, as a size, is 2/3. Like the negative just means that it's below the axis, but as a size, this area is 2/3. Now this graph is obviously symmetrical, so this area down here will also be 2/3. And this one will be 4/3, just like this one was. So all I have to do is add these two areas and times by 2, or add all 4 together, whatever you want to do. But 4/3 plus 2/3 is 6/3, which is 2. So this total area is 2, times it by 2 to get the total area of 4. A nice question, just make sure whenever you see total area enclosed, you don't just integrate across the entire width, because then your areas start cancelling and you don't get the total area. Okay, lovely ratio question, this one. I love this kind of thing. Making a table is probably the best shout here. So here's my table, type of paint, PQR, and whatever we're calling the mix, which it doesn't really give a name to. Now, if you're going to mix these paints in this ratio, I'm going to use my favorite ratio trick here, which is I'm just going to pretend you're using those actual numbers. I'm going to pretend you used 12 litres of P, 5 litres of Q, and 3 litres of R, which means, of course, your new mix is 20 litres of paint. Right? So I've literally just changed this ratio for actual numbers, which is a really useful little trick. And I can also extend that idea here. So how much red paint is in P? If I've got 12 litres of P, well, 30% of P is red. So all I have to do is work out 30% of 12, which means just doing 12 times 0.3, which is 3.6. You can also use fractions if you're more comfortable with fractions. It's up to you. Now the volume of red in Q, well, there's 5 litres of Q and 20% of Q is red. So 5 times 0.2 is 1. And now 25% of the new mix is red, and I've got 20 litres of that. So 20 times 0.25 is 5. But of course, this is the total. The new mix is the total, right? I added all these up to get my total paint, and I have to add up all these 3 to get my total red paint, which means the total red paint in R is 5 minus these 2. So there's 0.4 litres of red paint in R. But R is 3 litres in total, so to find the percentage that's red, I just do 0.4 divided by 3. And you can use a bus stop to do this if you want to. If you had been working with fractions, it probably would have been, you would have got a nicer answer in the end, but bus stop works here, and you know this is just going to recur. So the percentage times that by 100 is 13.3 recurring, which is this. Make sure you know how to do a bus stop, because otherwise this bit doesn't work so well. But yeah, really lovely question. Okay, question number 7, super easy question this. And I don't know whether I'm being maybe I'm being not very kind there, but anyway, apologies if you, I'm just imagining someone clicked this video just to watch question number 7 because they did everything else and I opened it up by saying it was easy. I apologize to anyone who's watching and for whom feels like that. Anyway, this one, again, my favorite trick when it comes to percentages or ratio or anything, make up a number. Literally just pretend there are 100 members of this club. If there are 100 members of this club, then there are obviously 60 women and 40 men, according to this line. If you've got 40 men and 2/5 of them play cricket, well, we know how to work out 2/5 of 40. That means 16 of them play cricket. Now, if 2/3 of the cricketing members are women, then that means 1/3 of the cricketing members are men. If 1/3 is 16, then that means that 3/3, or the total number of cricketers, is 16 times 3, which is 48, which means women cricketers are 32. Another way to think about that would be, well, if 1/3 of the cricketers are men and 2/3 are women, then that means there are just twice as many women playing as men. So you just times this by 2. Okay, now you either play tennis or cricket, which means of the 60 women, if 32 of them play cricket, then that means 28 of them play tennis. And then pick a member of the club, well, there's 100 of those, so it's just going to be 28 over 100, which simplifies to this. Yeah, make up a number is my favorite trick. Even if you had made up 100 happened to work here because it gave me lots of whole numbers, but don't worry if it doesn't. Like, even if you made up the number, let's say that you were weird and made up 7 members, you'd of course have got a fractional amount of women and a fractional amount of men, but that's fine. You can still run with it. You just have to pretend that you're okay with having 0.2 of a man or whatever. But it would still work in the end. So don't worry about what number to make up. Just use the most obvious one. But it would work in regardless. It would work in any case. Question number 8. Yeah, so just a straight up A-level question, this, I think. Maybe a bit harder than most A-level. If you ever see a quadratic in sine and cos, make sure it just becomes a quadratic in one of them. So replace the cos squared with a sine squared via this identity. Now, because I've got 2 x's in there, I'm going to actually use this version where I just replace the x's with 2 x's, which I'm allowed to do. Now I'm just going to replace cos squared of 2x with 1 minus sine squared of 2x in there, keep everything else the same. I think I times everything. No, I didn't yet. I times everything by -1, look. And then said 7/4 minus 1 is 3/4. That makes sense because 1 is 4/4, I guess. And then I think I times everything by 4 just because I didn't like this. Yeah. And now I think I flexed a little bit here. This factorizes, and it's quite difficult to spot. If you replace this sine squared 2x with just s, then it's easier to spot the factorization here. Now, I know it's unusual for me to have to try and factorize something with 4√3 in the middle, but because this is TMUA, I've done quite a lot of TMUA at this point, and I know everything, basically everything factorizes. So I was primed to look out for this. So this should definitely say s squared. I'm so sorry, but that's sine squared, so this should be an s squared, and that factorizes to this. So that should say 4s squared, and then this is the factorization because this makes 4s squared minus 2s√3 minus another 2s√3 makes minus 4s√3 or 4√3s, and then a plus 3 at the end. So the solution is this, which means this, obviously, and then s, remember, was that. So this is my new question. So I've boiled all of this down to just this, which is pretty good. Yeah, let's just say 4s squared. Apologies for that. So yeah, solving this then. Well, maybe your teacher has done this a different way. This is how I do it. I let this variable be z, and I ask this question instead. But I'm solving between this range. So if that's the range, and now I'm not solving with x anymore, I'm solving with z. I just need to make that middle bit z by timesing everything by 2. Sorry, make everything 2x by timesing everything 2, then replace it with a z. Maybe your teacher has done something similar to this, whoever taught you this. And now I'm looking for this answer in this range. So I'm going to draw a sign between 0 and 720. And then I should know off the top of my head that the principal solution of sine inverse root 3 over 2 is 60. Which means using then a bunch of symmetry, I know it's basically the answer is right here, but using a bunch of symmetry, 60 back from 180 gives you a next solution, and then 60 forward from 360 gives you a next one, and 60 back from 540 gives you a last one, which is going to be 480. So Z is 60 is the principal solution, 480 is the biggest. But of course, 480 is the biggest Z, and Z is equal to 2 times X, which means divide by 2 to get R240. If Z divided by 2 is X, if Z is that divided by 2 for 240. Yeah. Question number 9. So I immediately start drawing when I see this. 3, 3, 7, 5. Apparently they make a circle, and that's the diameter through there. I should have written it in, but I didn't. The diameter is through them, which of course means the midpoint of this circle is just, or the center of this circle, I should say, is just the midpoint of these 2 points, which is this. And now what's the radius of the circle? Well, I can just work out the distance from the center to the edge, which is going to be, well, 2 across from 5 to 7, 1 up. So the radius is root 5. And so the equation of this circle is x minus 5, y minus 4, squared, and then root 5 squared. Now I could write this as 5. I'm not going to, and I'll explain why in a second. Let's do these things then. So it's translated to 3 in the negative x, so 3 to the left. When you go 3 to the left, the center is obviously going to be brought to 2, 4, which means this is going to be x minus 2, and nothing else changes. When you reflect it in the x-axis, so the circle is currently centered about here, it's going to be reflected in the x-axis, so the y-coordinate of the center is going to go down to minus 4, and nothing will happen to the x. So if the y-coordinate is now minus 4, this sign is just going to flip to be a plus 4. Nothing else will happen elsewhere. And now it's going to be enlarged by a scale factor 4. Now what that means is enlarged about the center just means the entire thing gets bigger by a scale factor 4, which means the radius is now 4 times bigger. So the radius is now 4 root 5. And that's why I didn't square this yet, because if you did square this and just said this was 5, it's super tempting just to times the 5 by 4 to get a radius of 20. But this is not 20 when you square the new radius, which is actually 4 root 5. You do 4 squared, which is 16, times root 5 squared, which is 5. 16 times 5 is 80. So just be really careful with stuff like that. Essentially, you scale factor out by 16 because you're squaring the thing that you're increasing by 4. So you increase it by 4 twice, essentially. Okay, how many solutions does this have? I mean, this looks fairly complicated, so I'm not going to do it. I'm just going to say, I'm going to divide both sides by x, assuming x isn't 0, I guess. And then I'm going to say, well, what this is asking me how many times does this line, y equals tan x, intersect this? Because if you were asked, where does this and this intersect, you just set them equal to each other, and then maybe you times by x and you get the original question. I'm just working backwards. So I'm just asking, when does this intersect this? In fact, I'm not. I'm just asking how many times. I don't need to know the actual answers. Well, let's draw these 2 graphs. We should be able to draw both of these in this range. Tan looks like this. Quite difficult to draw, but you should be on top of that kind of thing, I think. If you're watching this kind of video. And then this is also easy to draw. And like I just have to count, like how many times are these things going to intersect if I was to draw them on top of each other, which I can do. But yeah, if you just draw this one over the top of this, you're going to get one solution about here, one solution about here. This solution is going to be just past 2 pi. And then if you put this line over the top of this, you're going to get another 2 solutions, and you get 4 in total. So yeah, if you just in your mind want to, or if you want to get some paper and draw these 2 over the top of each other, you can count how many solutions they have. It's going to be 1, 2, 3, 4. This solution and this solution, or intersection, are just off the range. So just 4 solutions. Number 11. This one's a little bit interesting. I'm going to first write the 4 as 2 squared. So that's all I've done there is just write the 4 as 2 squared because that's what it is. Then I'm going to multiply out this. And I'm also going to say, well, if you've got this kind of thing going on, I can just say that's 2 to the 2x times 2 to the 3, because if you have the same base and you're multiplying, you add these together. So I've just done that law in reverse, right? And now 2 to the 3 is just 8. So that's just 8 lots of this. And now here, what I've essentially done is I said, well, I can make 40x in another way. I can make it as 2x times 2. So I've put the 2 outside. Another way to think about this is, you know the law here for these powers, you multiply them together. Well, multiplying doesn't matter what order you do it in, so I'm just essentially just swapped these two rounds to get it to here, because you'd still just multiply them and you still just end up with this. Now, why have I done this? Well, because now if I just do a tiny bit more rearranging, I'm just going to move the 8 lots of 2 to the 2x over to this side. Now I've got this thing, 2 to the 2x squared, minus 8 lots of that thing plus 12 equals 0. This is a quadratic. It's something squared minus 8 lots of the something plus 12. Almost like x squared minus 8 lots of x plus 12. So it's just a quadratic. And again, this is TMUA, so I know it factorizes. If you want to make a substitution here, like let this equal y, to make it more easy for you to see, please pause the video and just do that. But I think I'm comfortable enough to just do this kind of thing without it. If we expanded this out, we get 2 to the 2x squared, because you're multiplying it by itself. Then we'd have minus 6 lots of 2 to the 2x, minus another 2 lots of 2 to the x, which gives you this, and then a plus 12. So this does work. And this, of course, means that either this is 0 or this is 0. We can solve these, either this or that. Take log to base 2 of both sides. Log to base 2 of 2 is just 1. Divide by 2 here, divide by 2 there, and we get our two solutions. Now, it's actually saying the two solutions are called P and Q, where P is bigger than Q. So which of these two things is bigger? Well, this one, I think, is bigger. And I know that because it came from this thing here. Now, if you're making 2 to 2x be a bigger number, then the x must be bigger. So this one is going to be the bigger solution. So that's going to be the P, and this is going to be the Q. And I need to do P minus Q. So these are my two answers, and I need to do P minus Q, which is this. Now, this doesn't look anything like these. And I also have a base 2 instead of a base 10, which is a bit annoying, but I can fix that. I'm first going to factorize out half. And now I'm going to say, I think, yeah, I am. What is 1 if not log to base 2 of 2? Now, the inspiration for this was because that's how I made the 1 earlier, if you remember. Like back here, this 1 came from log to base 2 of 2. So essentially, I've just put it back. And the reason I put it back is because that way I can make 1 log. Because now I can use the log law that if you take away, you divide the two numbers. So I get this. And this is looking okay, except I've still got a log to base 2, so now I need to use the change of base law, which I used a lot when I was a kid, but is not used so much anymore. If you've got log to base A of B, then that's log to base whatever you want, in this case Taylor Swift, of B divided by log to base Taylor Swift of A. And Taylor can be whatever you want her to be in this law. So it can be log 10, base 10, base 10. You just need to put this one up here and this one down here. So here I'm going to say this is log to base 10 of 3, log to base 10 of 2, with the half outside. Then I can expand the half back in. I don't know why I wrote the same thing twice there. Then I can expand the half back in, and then I can use the power law to put this 2 up as a power up here. And then, of course, 2 squared is 4, and I eventually end up with this. So sometimes it's a bit annoying. You get an answer that you're really happy with. Like, I'd have been really happy just leaving my answer like this. This looks fine. But in TMUA, double-edged sword of having multiple choice, you need to get it in the way that they want it. So that included doing some extra work. But anyway, it's E. Number 12. So we've got to imagine that this is a sphere with a cylinder inside it, kind of stuck inside, I guess. Now, we know the volume of a cylinder is pi r squared h, where r is the kind of the radius of each circle at the top and bottom of the cylinder. And h is obviously the height. Now we know the radius of this sphere is 5, which means if I call this length height divided by 2, which it is, then I can find a formula in terms describing r and h in terms of each other, just by doing Pythagoras. So r squared plus this squared is 5 squared from Pythagoras. I'm going to rearrange that to be, once I've multiplied that out, I'm going to rearrange it to be this. And now I'm going to put that r squared into here. Not going to bother square rooting it because I can see a nice r squared right there, so I can put that straight in. So that's my volume formula. I can expand that out. And now I can differentiate that, right? When it's talking about the maximum possible volume or minimum possible. You're talking about differentiation. So now my only variable is h, which means I can happily just find the derivative in terms of h. So yeah, that's the derivative of that. This is the derivative of that. And I'm trying to find a maximum, so just going to say the derivative is 0 maximum, and then I can solve this. I think I divided both sides by pi, move this thing over. I think I can times by 4, divide by 3, and I get h squared as that. And then I can square root for h as this. No need to worry about the plus minus because these are lengths, so they're all positive. Now that's the height when the volume is at a maximum, but that's not the maximum volume. The maximum volume is when you put that height back into the volume formula. So let's take this volume formula. I guess I used this one for some reason. I don't really know why. Oh, I know why I use this one. It's because I have an expression here for h squared, which can go right in there. And I have an expression here for h, which can go in there. So that's why I use that one. And then h squared divided by 4 is just 100 divided by 12, because you just times this number by 4. And yeah, then you work through it. Make those fractions the same, do that. Still got some work to do, I guess, because I noticed that these are all rationalized. That's annoying. Yeah, simplify that fraction, I guess. Cancel 2's here to get that, yeah. Then we can finally expand out. And now we need to do some rationalizing. Times both sides by, or top and bottom by root 3 over 3. This becomes, those two become 3 when they're together. Times by 3 to make 9. And then, yeah, and I think that's one of the answers. Good. Question number 13. How many roots? Very step-like this question. If you're aiming for a top 5 university, this is the kind of question that you just need to have down. Like, you want to be able to do this kind of thing in your sleep. This is a quintic equation. So, and it's a positive, so it starts way down here and ends way up here, just like a cubic would. And we also know it goes through the y-intercept of 30. So those are the things I immediately know. Now, I want to know how many times it kind of goes up and down, and how many times it passes through the x-axis, because that's what the roots are. And to find out how many times it goes up and down, I guess I'm going to find its turning points. So if this is the function, find the derivative, set the derivative to be 0 to find the stationary points. And now I notice this is a lovely quartic, but it's actually a quadratic in disguise. If I divide everything by 15, it becomes very clear that I can factorize this, again, because you can factorize basically everything in TMUA. Multiply those two out to get x to the 4, minus 4x squared plus 2x squared makes minus 2x squared, and then minus 8. So either x squared plus 2 is 0, or x squared minus 4 is 0. Now that has no real solutions, because you can't square something to make a negative if you're in the real numbers. This does have solutions, it's got plus minus 2. So I've got two stationary points at x is plus 2 and x is minus 2. Now what I want to know is I want to know where the function actually is at those 2 points. So I'm going to find f of 2, and I'm going to find f of minus 2. Now I'm just being incredibly lazy here. I'm going to put 2 into here to try and find essentially the y coordinate. But I'm not even going to bother with this, because I can tell from this number here that this is going to be negative. So the turning point at 2 is going to be somewhere below the axis. Whatever number it is, I don't really care. What I tend to do is put a line through the points that are stationary, just so I remember when I sketch this curve, it goes flat through there. And likewise, I'm going to do the same for minus 2. So I'm going to find the point where it's minus 2. I can again see that this is massively going to outweigh this. That gives me a positive number. I can also see that it's above 30. So this stationary point has to be above 30, above the line somewhere. And now this is all that the curve can really look like. It can't turn any more than these 2 points. And so it can only have these 3 roots, roughly. Okay, number 14. Yeah, a bit of a weird question, this one. You've got an infinite series S, which is formed by adding together 2 infinite series T and U. So let's say T starts with 4. Both T and U start with 4. Now they're geometric, so you times by something to get the next term. So I'm going to call the next term 4r, and the term after that 4r squared. And likewise for U, starts at 4, but I can't say it's r again, because I don't know that the geometric series multiplies by the same thing for each sequence. So I'm going to call it k, and then 4k squared. Now, of course, S is the sum of these 2 sequences. So the first term of S is 8, and then the next term it says is 3, and then 5 over 4. But of course, if it's the sum of the first 2 sequences, then that means 4 plus 4 is 8, which is a revelation to all of us, I'm sure. But more importantly, it means 4r plus 4k is 3. And it means that 4r squared plus 4k squared is 5 over 4. Now, this is a simultaneous equation. And I paused for quite a long time here, trying to figure out what the nicest way to solve this simultaneous equation was. Like, I want to know what R and K are, essentially, because if I know what R and K are, I can put them into here, and then I can just add up each geometric sequence separately. It's asking me for the sum to infinity of S, but this isn't just a standard geometric series, so I can't use the formula for it. So what I'm going to do is I'm going to find R and K, put them in when I find them, and then just sum up T and U separately, and then add the results together to find S. So how do I find R and K here? Well, I decided that I'm going to times both sides by 4. And then I decided that I was also going to square both sides of this equation. Okay, which is not an obvious step to do, but it's just because I really didn't want to work with annoying fractions or anything like that. If I square this out properly, I get, well, you put a bracket next to it of the same thing, 16R squared, 4K squared at the end, then you've got these middle terms of 16KR, two of them, so that's 32KR. And the reason I've done this is because I've noticed that this term plus this term, according to this, makes 5. That's just this term and this term together make 5. So that means that 32RK is 4. And what I've done here is I've reduced this part of the simultaneous equation. I was working with this and this, but what I want to do is I want to work with this and this, because they seem more pleasant. So I'm going to forget this horrible looking quadratic, and I'm just going to work with these two things instead. And I'm going to solve them. Of course, if I rearrange this, I get that. And now, what is 32RK if not 8K times 4R? And I'm just going to put the 4R in. And this gives me a lovely equation in K, which I know I can solve. So I'm just going to solve it. Again, it's TMUA, so you know this factorizes. Eventually you find it. And now you've got two answers for K here. And now this is annoying because going all the way back, this is a dangerous step, this one to here. This is dangerous because when you square stuff, occasionally you add in extra solutions. And if you're used to doing TMUA paper 2, you've seen that kind of mistake being made by students in the spot the mistake questions. So it's tempting to say, oh, well, maybe one of these solutions isn't okay. Maybe I created a false solution when I squared. That's actually not what's going on here. What's going on is when you go back into the equation, when you try and find R by just going into one of your equations, when you put in K as a quarter, you get R as a half. And when you put in K as a half, you get R as a quarter. So all this is saying is that it didn't matter which order I wrote R and K here. Like I could have made K the first sequence and R the second, or I could have made R the first and K the second. It doesn't matter. It's just one of them is a quarter and one of them is a half. But because it's a nice symmetrical problem, it doesn't matter which. So one of R one of R or K is a quarter, the other is a half. It doesn't matter which. I'm just going to choose R to be a quarter. So this term is 1, and this term, or a quarter squared, is a 16th. Times by 4 is a quarter. And then I'm going to choose K to be a half. So this sequence goes 4, 2, 1. And then I'm just going to check that it works, and it does. 4 plus 4 is 8. 1 plus 2 is 3. This plus this is 5/4. Good. So I found the correct thing here. Now the infinite sum, nice. The infinite sum of a geometric series is this, where A is the starting term and R is the ratio, is the thing you multiply to get from the other. So all I have to do to find the sum to infinity of S is do this infinite sequence, the sum of, plus this one. So just do them separately. So here we've got 4 as the starting term over 1 minus a quarter. That's 3/4. Bounce the 4 up to get 16 over 3. This one, starting term is still 4. This time the ratio was a half. That's a half. Bounce the 2 up to get 8. And then add these things together. 8 is 24 over 3. And that's going to be 40 over 3. And that's going to be the sum of S, which is just the sum of T and U. And that's going to be our answer. Question number 15. Talking about gradients, so I know I'm going to have to differentiate this. Now, I could have done this using product rule, but I'm not convinced that everyone watching this will know what product rule is yet. So I decided to just expand all this out, even though it's painful. We should be able to do this thing. So yeah, expand it out, then do the differential. Which is going to be this. Remember the A's, you don't differentiate this like a normal thing, like you would differentiate X. A is a constant. So this just goes away when you differentiate. And likewise, these don't become 2A's or whatever. You just differentiate the X, but everything else is just a number. Now, this is at the point X is 1. So I'm just going to put X as 1 in, which is nice because nothing happens. You just, simplify that up. And it's now asking me to minimize this. It's asking me to minimize the gradient at X equals 1. So I'm just trying to minimize this thing here. Now I could differentiate this again, but I notice it's quadratic and I know how to find the minimum points of quadratic, so I can complete the square. So I'm going to complete the square. I'm going to rewrite it like this. I'm just going to take a 4 out of just the a's and leave the constant alone. It's just that I don't have to deal with as many fractions. But I can complete the square on this inside bit, halve this number, put it in a bracket, so half of 7 over 2 is 7 over 4, square it, take away the square of this thing here, and now I can sort this out. That's 49 over 16, times it out by 4, so now I'm putting the 4 back in here, and now the minimum of this thing here is going to be this. It's going to happen when a is 7 over 4, but the minimum is this bit here. So I'm going to put those together. 6 is 24 over 4. Add those together to get minus 25 over 4. Cool. Question number 16. Nice log question, this one. I know the log law says that I can put these two things together if I multiply. So the first thing I'm going to do here is I'm going to multiply the 2 by the y minus 1 and put them under the same log. I'm also going to move the 2 log to base 10, that should say, of x over to this side. I wonder how many mistakes times that's made. That's annoying. This should say 10. I haven't done anything to this log other than move it to this side of the equation. That should be a 10. That should also be a 10. And now all I've done with that 2 is just move it up to here. So apologies for that mistake, but I think I'm making it clear, as long as you haven't got this on mute, that that should be a 10 and that should be a 10. I did not intend to change those to log base 2. But anyway, now that I've got this log to base 10 minus this log to base 10, I can divide this by this, because that's what happens when you take away logs. So I can get this expression. And now, okay, there's an easier way to do this next bit, but I do it here anyway. What is 0 if not log to base 10 of 1? And now I can just compare that the inside of this log to base 10 must be the same as the inside of this log to base 10. So that must be the case. This just must be 1. And then I can times both sides by x squared and I get this. I'm going to pause there. What about this side? Well, again, I could write 0 as log to base 10 of 1, or I could just be a normal person and raise both sides of this equation to the power 10, or 10 to the power of both sides, because then the 10 to the power of log 10 cancels, 10 to the power of 0 is 1, and you get the same kind of idea I was going with here. Now, again, I paused here and thought deeply about my next move, because there's ways for this not to go well. Now, I'm looking at the answers here, and I'm worried that I'm not going to get something nice. So when it says the values of y, I think I'm best off making sure that I find y first. This is a simultaneous equation, again, but if I found x, then I'd have to then substitute in to find y. But because these numbers possibly aren't nice, I'm going to find y. That means I'm going to isolate the x's. Now, how am I going to do that? Well, I'm going to move the 3x over and then take away 1 from both sides to get this. And again, I'm going to do something a bit weird here. I'm going to times this equation by 9. Why am I doing this? Well, because I can write this bit here as 3x brackets all squared. And this ensures that I don't mess around with any fractions or anything like that, because I can just put this lovely expression for 3x straight into there to get this, and this is just a quadratic in y, no fractions to mess around with, really nice, can do this very quickly. This doesn't end up, I was right, this doesn't end up being a nice number, and this is why I made really sure to solve for y, because if I'd been trying to solve x's and I got some surds, then putting in them in to find y would have been annoying. So I made sure to find y. I'm going to do this by completing the square, and I hope we're all okay with this kind of thing, and I get the answer. Now, root 27 is, well, 27 is 9 times 3, so that's root 9, root 3, which is 3 root 3, and I get my answer. Cool. Number 17. So I want y to be negative. Notice how y is this thing multiplied by that thing. So y is a product of two things. Now, if I want y to be negative, there's two ways to make a negative through a product. You can either make the first thing negative and the second thing positive, or the other way around, right? So I either want this to be negative and this positive, or this to be positive and this negative, right? So, and now I need to do each case individually. So taking this one here, take away 1 from both sides, divide by 2, and I want cos to be greater than minus half. Now, if I draw the cos graph between 0 and pi only, that just looks like this. And I want cos to be greater than minus a half. So I want the angle to be less than this, whatever this is. Now, we should know when cos is minus a half, and it's minus a half at 2 pi over 3. Now, if you're a little bit unsure about that, you should know that cos is a half at pi over 3. So if it's pi over 3 this way to get to a half, it must be pi over 3 backwards symmetrically as the sine and cos graph are to get to here, and pi minus pi over 3 is 2 pi over 3. So that's going to be my range where cos of x is greater than minus a half. It's between 0 and pi over 3. Sorry, 2 pi over 3. Now looking at this one, because I also need this to be true, because I need this to be positive and this to be negative. Well, let's draw the cos 2x graph. That's just this graph squished in by a factor of 2. Now, when is this less than 0? Well, clearly when x is between these 2 points here. Now, where are these 2 points? Well, notice how the cos x graph crossed the x-axis at pi over 2. This graph has been squished in by a factor of 2, which means this must be the point pi over 4, because it's just this point squished in by a factor of 2. So pi over 2 to pi over 4. And again, symmetrically, this must be 3 pi over 4. So that's when the graph is less than 0, this one here. And comparing these two things, when am I in both of these ranges? Well, 3/4 pi is slightly bigger than 2/3 pi. So this is my lowest, biggest bound. And this here is my biggest, lowest bound. So it's got to be between these two. So I know it's between this and this as my two answers. Now I suspect it's this, because I suspect this is going to give me a similar thing, and this doesn't have anything attached to it. So I suspect the answer is this, but let's just double check. I need 1 plus 2x to be less than 0. Well, this is just the symmetrical case, right? It needs to be the opposite answer to what I got the first time. I need cos x, when you do the maths, you do the same maths here, you just get the sign the other way around. And I need cos x to be less than minus a half. Well, that's just going to be when pi is greater than 2/3. When x is greater than 2/3 pi, right? Like, it's just a symmetrical case of this. And I guess less than pi I should have put, but it's not going to make a difference. And likewise, this is going to be the opposite case to before. So either x is between pi and pi over 4, sorry, between 0 and pi over 4, or between 3 pi over 4 and pi. And again, comparing, when are you in both of these things here? Well, this doesn't work because you have to be bigger than this in this kind of world. So this is my lowest bound, except it's still not, because I still have to be bigger than this. So in fact, all that matters is this bit, right? Because if you're slightly bigger than 2/3 pi, you're still not big enough for this range. So it's just going to be this range, and combining the two, we get this thing here. Question number 18. Cool, so the first thing I do is write the cube root as a power of a third, then I multiply out. And I know this because when I see the word decreasing, that means talking about gradient. So I know I'm going to have to differentiate this. So I don't like this notation. I prefer this notation. I'm going to do this divided by this for that, and this divided by this. That's an x to the power 1, and 1 minus 2/3 is 1/3. And now I differentiate to find this horrific thing. And now a function is decreasing when its derivative is less than or equal to 0. So I want this thing to be less than or equal to 0. And this looks disgusting, but I think I can work with it. I'm going to factorize out an x to the power minus 5/3. Now this looks really crazy. And I'm also going to factorize out a minus a third, you notice. And now just check that this expansion works. When I expand this first bit, I'm going to get minus 2/3 this, which is fine. And the next bit, I'm going to get minus 1/3. And now this is an x to the power 1. And 1 plus minus 5/3 is minus 2/3. So this works. And now I've got a very similar thing to what I had before. I've got this thing multiplied by this thing needs to be less than 0. So I'm going to do the same kind of thing I did in the last question. I mean, first, I can times both sides by minus 3, and then I end up with something slightly better. And this time I'm looking for it to be greater than 0 because I times by a negative number. But again, this is the same as before. I've got this thing multiplied by this thing greater than 0. So either I want them both to be positive, or I want them both to be negative, right? So I either want this to be positive and this to be positive, or them both to be negative. So I want, this graph is spoilers, I guess, but whatever. So I either want this to be greater than 0 and this to be 0, or I want them both to be negative. Now, the thing about this here, I mean, this one's easy, right? You just take away 2 from both sides, and I want this. This one's a bit more difficult, but if I cube both sides, cubing 0 does nothing. And also, I'm allowed to cube both sides with an inequality, because if you cube a negative, it's still negative. And if you cube a positive, it's still positive. So the inequality is going to be fine. That's a bit of a hand-wavy argument, but the inequality should be fine. And now this is just like a skewed version of the 1 over x graph, the x to the power minus 1 graph. So this graph looks a bit like this. Essentially, when x is positive, it's positive, and when x is negative, it's negative. So for this to be true, I just need x to be greater than 0. Greater than, not equal to, because when x is 0, it goes a bit weird. But I just need x to be greater than 0. And you can try some numbers to test that, but it's true. So putting these together, I get, well, x can't be greater or equal to minus 2. Like, this one is irrelevant, right? Like, if you're greater or equal to 0, if you're greater than 0, you are this. And if you're this, you're not necessarily this. But if you're minus 1, then it doesn't matter because you have to be this anyway. So this is the only thing that matters here. So that's my first bit. But I could also, just like in the question before, I could either be less than 0 on both of these products. So I could be less than 0 on both. And this is exactly the opposite of this bit. And this is, again, nice and simple. So I have to be less than 0. But again, I also have to be this, so this doesn't end up mattering. So my two conditions are less than or equal to minus 2 and greater than 0. That's my answers. Almost there. Question number 19. Okay, I have done this one. Just full disclosure, before you watch this, I've done this in a really stupid way. And I don't know whether it is a stupid way, but it's the first way that I thought of, and I stuck to my guns. I'm talking about expanding this thing here. Now, expanding something with 3 things in it is not as easy as expanding something with 2. So this bit ends up being much easier. But what I said here was that, okay, so this is this bracket multiplied by itself 6 times. And how I think of expanding brackets is you kind of just choose something from this bracket to take, like the 1. Then you choose something from this, then you choose something from this, then you choose something from this, then you choose something from this. And you kind of bounce along the brackets, just randomly choosing one of the things to take. And that's kind of how you expand brackets, right? Like you just choose one from here, then this from here, and then you choose all the possible things you could, one by one, and then you add all the together everything that you get, and that's your expansion. So how are we going to get a coefficient of x cubed out of this? Well, either I bounce along 3 1s, and then 3 2x's. That's going to give me an x cubed term, right? 3 1s just give you a constant, and 3 2x's give you 8x cubed. So that can do it. And that's going to be 6 choose 3 because I'm choosing 3 1s. I'm also choosing 3 2x's as it happens. But I'm choosing 3 of the 1s to take. Then you just do the raise each thing that you're taking to the power of how many times you're taking it. And now 6 choose 3 is done by this if you don't have a calculator. So it's 6 factorial over 6 minus 3 is 3, and then k is just 3. And then 3 factorial is 3 times 2 times 1. So you cancel this 3 factorial, all of that. And then you do 6 times 5 times 4 divided by 3 times 2 times 1, which ends up being 20. And of course, 2 cubed is 8, and you get 160. And so you get 160 x cubes by bouncing along 3 1s and 3 2x's. Of course, this thing here comes from the fact that you don't just get this by doing these 3 1s and then these 3 2x's. You could also get this 1, this 1, this 2x, then this 1, then this 2x, and this 2x. And it's all the possible combinations found by this term. Now, there is another way to get an x cubed term, which is to take 4 1s, so bounce along 4 1s, and then take a 2x and a 3x squared. So it's tempting to say, okay, this is just going to be 6 choose 4 for your 4 1s, and then you're going to have 1 2x and 1 3x cubed term. But that's not quite what it is. You also need to shove an extra 2 here. And the reason you need to do this is, again, because expanding something with 3 terms in it is a bit more complicated. And essentially, you can think of where this 2 comes from as, well, if you take these first 4 1s, and then a 2x and then a 3x squared, that's one combination, but you can also then flip the order that you take the 2x and the 3x squared in. Like you could then instead do the 4 1s, the 3x squared, and then the 2x. So it's going to be twice as many of everything because you could swap those last 2 things around. And then you just take 1 2x and 1 3x squared. And it's nice, I've just put the x's in to justify that, yeah, that is an x cubed, and that's also an x cubed. But 6 choose 4 from this will give you 15. 2 times 15 times 2 times 3 is 180. Add those 2 things together, and you get 340. And I think that's the only way to make an x cubed from this. Like, I don't think you can use any other combinations. Otherwise, you just get too high. So we've got 340 x cubed from here. Now, this one's much easier to deal with. Where are we going to get x4s? Well, it's just taking 2 of those and 3 of those, right? And of course, the combinations have to add up to 5. So you just take 3 1s and 2 of those. So I'm going to do 5 choose 3, and then 1 to the power 3 because I'm taking 3 of those, and minus ax to the power 2 because I'm taking x. That should be an x squared. I'm so sorry. That should be an x squared. I'm taking 2 of the ax squared terms. So that should be minus ax squared, all to the power 2 because I'm taking 2 of them. 5 choose 3 is the same as 5 choose 2. And you can pause and figure out why just by looking at this, which is why it doesn't matter whether I choose 5 choose 3 or 5 choose 2. And that should be an x to the 4, again, because that should be a squared, so times together should give you an x to the 4. And in any case, you get 10 is your answer. And so, essentially, and I still don't know why, oh, sorry, that shouldn't be an a to the 4, that should be an a squared, because that just comes from a squared. And then I've ignored the x's, because I don't need them anymore. And now, what I'm saying is that I've got twice, this is equal to 2 lots of this coefficient. Now this coefficient is 10a squared. So 2 lots of 10a squared is 340. That multiplies to make 20, divide by 20 to get this, and then you square root to find plus minus root 17. Yep. 20. Really interesting question, this, to finish off. I immediately don't like these answers as soon as I see them, so I'm hoping it's not them. Okay, so you've got this square-based pyramid, and you're told that every side is 20, which is nice. And you're trying to get from P to the midpoint of OR. So you're trying to do this journey here coming out the page. Unfortunately, you're not allowed to go through the pyramid. You have to go around the outsides. Now, we'll call this point M, where for the midpoint of OR. And of course, that means that this length is 10, and so is this length. Now, I can see a few routes around the edge to get from here to here. I could go on the edges themselves. I could go up 20 and then down 10, and that would make a route of 30. But I'm pretty sure I can do better than that. Because like if you snake around this face here, like if you go along this face, kind of gradually rising up, and then along this face, that looks better, right? That looks much better than going up here and down here. And I can prove it because if you turn the pyramid to look like this, so I've turned this pyramid, rotated it around so that we're looking bang on this face S to make it look like a triangle, a 2D triangle. What I'm saying these two routes are is I'm going along this face which is now kind of on its side, along this face, and then in as straight as line as possible, I'm going to M. And that's definitely going to be better than going all the way up here, which is 20, all the way down here, right? So I can discard the idea that this is the best route, up 20, down 10, because along here and then along here must be much faster. But there is one other route I can take. And by the way, I could do that route along any of the other faces. I could go along here and then along here, and it would be symmetrically the same, right? If I went along there and then along there. That would be the same kind of thing. But there is another thing that is different, which is, and not so obviously wrong, which is I could go along the base of the pyramid and then up this side here. Or likewise along the base down to here and then along this side, but that's also symmetrical. So I could go along there, right? Along the base up this side, this front side, or along this base up this side, but that's the same thing. And it's not obvious which of these routes is better. Now, to work out the length of these routes, what we can do is we can look at the plan of the shape. And now I only know how to do this because I've seen problems like this before. And this is why practicing maths is so important, is because if you haven't seen this before, it's very difficult to come up with this kind of idea. But this is the plan of my pyramid, right? If I just draw it out nice and flat. And the reason it's so good nice and flat is because I know exactly where I'm going to here, between R and O, halfway. And I know I just want to go along this straight line. So this is the green route I'm doing first. I've opened out this pyramid into a plan, and I'm just going along this straight line, straight down to where this point ends up when you flatten the shape out like this. Right, so I'm just going straight along to here. Well, in fact, am I actually going... I should have drawn it to here, but it doesn't make a difference. Yeah, I should have definitely drawn that to here, but it doesn't make a difference. It's as if I'm now going... I think we can tell that this is going to be the same length as this. I'm going to leave it because I've recorded this much already. But yeah, we can tell that this journey is going to be the same as this journey. It's just symmetrical, right? So that's fine. Regardless. In fact, no, I am okay to do this because when you close this shape up, of course, this point and this point are the same point. Yeah, I'm being an idiot. That's why I did it like this. It's the same. Good. Okay, I would have been annoyed at myself, but no, that's fine. So I'm trying to get to here. And now I know this length is 20. I know this length here is 20, and I know this length is 10. I know this angle is 60, because it's an equilateral triangle, because 20, 20, 20. This angle is obviously 90. Now this length here, this length I know is 20. This angle, by the way, is 30, because it's half of the 60. Now this blue length is just going to be, well, it's 20 squared minus 10 squared. I'm going to do that quite quickly. It's 10 root 3. Pause the video and do it yourself if you want to. But now I just have this triangle to look at. And I'm looking for this length. And I know as soon as I see this that I can do this. It's just cosine rule. And I know cos of 120, so that's fine. So I can do this, I think. Before I do, though, I am going to work out the plan of the red journey. Because I don't know whether the red journey is more or less. So I may as well just quickly draw the plan of that. And now to do that, I'm going to draw the plan slightly differently. I'm going to do the plan like this. Now notice if you close this up, all I've done here is I made this triangle close down here. I'm sure you can imagine it. It's hard to describe. But again, I'm trying to get from P across to this point M. And again, I could have drawn this differently, but this is fine. Like this side lifts up, then this goes next to it, and eventually this point connects down to this one, which is why it's the same as it was before. But I'm going along these two triangles to get to M. Now I know this length is 20, I know this one is 10, this angle is 60, and so is this one, which makes this whole angle 120, which means this triangle just looks like this, and I'm looking for this length across here. Now this is 10 because it's just the midpoint of this length. Now, just looking at these two triangles, I know which of x and y are smaller. I know y is the smaller one, and I'm looking for the shortest distance. I know y is smaller because these two triangles are identical, except that this side is longer than this one by a factor of root 3. And of course, as this side is longer, then the opposite side is also going to be longer. So I know this is the shorter route. So the shortest route is going along here, not going along the base. So this is the shorter, or again, going along the corresponding symmetrical distance. But this is going to be the shortest. I can do cosine rule here. The last tricky thing on this paper is knowing what cos of 120 is. But I mean, if you know what cos of 30 and cos of 60 are, then you shouldn't be too bad to work this out. Eventually you end up with minus a half, because cos of 90 is 0, of course, so that's when it starts going down. You've got another 30 degrees to go. I mean, however you want to figure it out, it's minus a half. This has 170. When you square root that, you're eventually going to get 10 root 7. I'll leave that to you. But yeah, really well done for sticking through me with that. A nice paper.